Okay, so in this video we're going to start talking about the last major concept in this unit, which is the concept of potential difference. And so just to start this discussion, we've talked in the past about the electric force, the Coulomb force, that acts between charged particles. And we've talked about the electric field, which is created by charged particles, which is the mechanism by which electric force is transmitted. Okay, and so today we're going to continue on in that discussion. So if you have an electric charge in an electric field, which has been created by some other charge, that electric charge will experience a force. Okay, and so that means that if you have a charged particle and you move it while it's acted upon by the electrical force, that means that work has to be done. So last year we talked about work, and just to remind you that the work done by a constant force is given by the equation Fs cosine theta, where F is the force that's acting, S is the displacement of the object, and theta is the angle between the force vector and the displacement vector. Now, typically speaking, in more general terms, the work equation is given by an integral, but as long as the force is constant, the work done by force is given by this equation. Now, the concept of work is important for you to know for this unit. So just to review what the concept is, when we talk about the work done by a force, we mean that energy is being transferred to or from that object by a force. Okay, so keep that in mind for what we're about to talk about. We're going to introduce the concept of potential difference. And the way we're going to define it is that the electric potential difference between 2 points is the amount of work done per unit charge in moving a point charge from A to B. Now, here's what I mean by that. Let's say we have this big charge over here, Q. Okay, this big old thing, this is a big old charge, and it's creating an electric field. Little q clearly is going to experience a force due to the electric field created by big Q. Okay, so the potential difference between point A and point B in this case would basically be the work needed to bring the charge from A to B divided by the value of the charge Q. Okay, and this is what we call electric potential difference. I'm going to write that as delta V. Here on this slide they write potential difference as V. I always think it makes more sense to write potential difference with a delta V so that you think of a difference between 2 points. And if you want to be more specific, it's the difference between the potential at B minus the potential at A, and that is what we call the potential difference between point A and point B. And that is the work done per unit charge in moving the charge from A to B. Now, you might be asking, what is V? I haven't told you what potential is exactly. Okay, so we'll come back to that concept in just a second. But this is how potential difference is defined: is the work done in order to move the little q from point A to point B divided by the value of that little charge. Now, the unit for work is the joule, because work is the transfer of energy, and the unit for charge is Coulomb. And so the unit for potential, or potential difference, is joules per Coulomb, but we give that a special name, and that is what we call volts. And so if you've ever heard of volts or voltage, that is the unit for potential difference. Okay, so a lot of people will say voltage, but what they're really talking about is the potential difference between 2 points. Okay, so the units for electric potential and potential difference are volts. Okay, potential is a scalar, and again, I have not told you what potential is. I've only told you how potential difference between 2 points is defined. Okay, so when I say VB, I mean the potential at point B, and when I say VA, I mean the potential at point A. And when I say the potential difference, I mean literally the difference between those two quantities, but I haven't told you what electric potential is yet. We'll come back to that in just a second. Okay, but the potential difference between 2 points is defined in this way. And again, W is the work needed to move a charge from point A to point B. Okay, and the reason work has to be done is because there is, like I said, an electric force acting on the little q. Okay, so pause there and add to your notes. And we'll come back to what exactly electric potential is here in just a minute. Okay, but using this definition, let's do a quick example. So let's say we have a charge of 15 microcoulomb, and we move it from point A to point B, and we're told that the electric potential at point A is 18 volts, and the electric potential at point B is 25 volts. Okay, I still have not told you what electric potential is, and I don't want you to get the wrong idea. I'm not misspeaking. It's not potential energy. It's potential. Okay, there's a difference between potential and potential energy. And again, I'll tell you more about what potential is in just a second. They're related concepts. But again, we'll come back to that momentarily. So I'm telling you that point A has a potential of 18 volts, and point B has a potential of 25 volts, and I take my little q and I move it from A to B. Okay, now question A says, what is the potential difference undergone by the charge? Well, the potential difference between point A and point B would be the potential at B minus the potential at A, and that would just be 25 minus 18, which is 7 volts. And so I would say there's a potential difference of 7 volts between A and B. Okay, now question B says, what is the work done in moving the charge from A to B? Well, the way potential difference is defined, I will remind you, potential difference is defined as the work done per unit charge in moving a charge little q from point A to point B. So in other words, the work needed to move the charge from A to B would just be equal to Q times that potential difference, delta V. And so that would be 15 microcoulomb. Actually, let me write it over here where I have more space. That would be 15 microcoulomb, 15 times 10 to the negative 6, times that potential difference of 7 volts. Okay, and so 15 times 10 to the negative 6 coulomb times 7 volts, that's going to give me an answer in joules, because that is the SI unit for work. And so I'm just plugging that into my calculator now, and I get 1.05 times 10 to the negative 4 joules. Okay, so that is the work done in moving the charge from A to B. Now, you're probably confused at this point because I still haven't told you what potential is. Okay, so here's basically what electric potential is. You can think of it kind of sort of related to potential energy. Okay, so the analogy we're going to use is we're going to go back to using gravity as an analogy. Okay, so let's say I'm holding a ball in my hand. If I want to lift it up into the air, I have to fight against the gravitational force. And so in order to lift a ball up into the air, I have to do a positive amount of work. In other words, I have to add my energy to the ball. Likewise, in this example here, we're moving a positive charge from a lower potential to a higher potential. Okay, in other words, we're fighting against an electric force, and so in doing so, we have to do a positive amount of work, and that's just what we've calculated right here. Okay, so pause it there, add that to your notes, and then we'll talk more about electric potential. Okay, moving on. Okay, so go ahead and add this to your notes. Okay, so the electric potential, which I'll now talk about, is closely related to electric potential energy, which we're not going to talk about electric potential energy explicitly in this unit. It's taught in AP physics, but not really in IB physics for some reason. But you can think of electric potential as the electric potential energy per unit charge. Okay, in other words, it's related to electric potential energy, but you divide out the charge. Okay, a potential difference delta V between 2 points A and B essentially means that either A or B is at a higher electric energy level than the other. Okay, so what I'm saying is that if you have a positive charge is going to feel an electrical force compelling it to go from a higher potential to a lower potential. The analogy, going back to gravity, is that if you have an object with mass is naturally going to feel a force compelling it to go from a higher point to a lower point. In other words, things fall down. Okay, now everybody knows if you drop a ball, it's going to fall from high to low, because that's how gravity works. The electric force is slightly different because you have positive charge and negative charge. And so if you have a positive charge that's out there in space, it's going to feel an electrical force from a higher potential to a lower potential. If you have a negative charge out in space, it would feel a force in the opposite direction. So in other words, a negative charge, if you just put it out there, it's going to try to fall, if you will, to a higher potential. In other words, a negative charge feels a force from a lower potential to a higher potential. Okay, now this picture right here is just kind of showing you the analogy with the gravitational field and with the gravitational potential. And so what we're seeing right here is we're basically seeing lines of gravitational potential, not potential energy, because in order to have potential energy, you have to have an object. You have to have a mass that actually has that amount of potential energy. This is so if you want to kind of think of it as the analogous between electric force and electric field, in order for there to be an electric force, you have to have two charges. Okay, an electric field can exist in space whether or not there's actually a charge at that point. In the same way, it's similar between potential energy and potential. So off to the side here, you see these numbers: 9.8 joules per kilogram, 19.6 joules per kilogram, 29.4 joules per kilogram. These are units of gravitational potential. In other words, if I'm holding a ball, let's say a 1 kilogram ball, right here at this lowest line, it would have 9.8 joules of potential energy. Because this is joules per kilogram, so if I have a 1 kilogram ball or 1 kilogram box or something, if I hold it at that point in space, it's going to have 9.8 joules of gravitational potential energy. If I don't have a ball, there's still some amount of energy associated with that point in space. Okay, because if I whip out of my pocket like a 2 kilogram ball, it's now going to have 19.6 joules of gravitational potential energy at that same point in space. So whether or not there's actually an object there, there's still the potential for an object to have potential energy, if that makes any kind of sense. Okay, so likewise, there's the concept of electric potential, where if I have a charge out in space and I put the charge there in space, it might have some electric potential energy. If I don't put a charge there, there's still the potential for electric potential energy to exist if I did put a charge there. Okay, and if that is confusing to you, you're definitely not alone. When I was in school, this was easily one of the most difficult concepts to understand, the concept of electric potential. And so I apologize if this doesn't make any kind of sense. I'm doing my best to explain electric potential. Okay, so let's move on. I'll tell you some facts about electric potential. And I think I said these before. The symbol for electric potential is a V. Okay, electric potential is a scalar. The units for electric potential are the volts. Some other facts that you need to know. If you have a zero electric field in a region of space, the electric potential there is constant. And then most importantly, electric field lines, which we've talked about the concept of the electric field before, always travel from areas of high potential to low potential. So on the last slide, I showed you pictures of gravitational potential lines. In other words, these would be lines of these would be what I would call gravitational equipotentials, or lines where the gravitational potential is the same everywhere. And if you were to sketch in the gravitational field lines, they would look something like this. Okay, the gravitational field would go down towards the ground, and they would always be going from a high gravitational potential to a low gravitational potential. In the same way, electric field lines always point from high electric potential, to low electric potential. Okay, now let's go back and talk more about electric potential. Electric potential difference. We know if there is a potential difference between 2 points in space, there has to be an electric field between those 2 points. That electric field is always going to go from high potential to low potential. And that concept, by the way, is going to be important in the next unit that we do, or not the next unit, but the one after that, circuits. Because when we talk about circuits, when you talk about voltage, voltage is potential difference. And so when we talk about what drives current in a circuit, yes, it's a battery, but fundamentally it's a potential difference. And we'll talk more about that later on. Okay, but if I have a positive charge in my pocket, if I want to move it from a low potential to a high potential, I have to do a positive amount of work. We talked about that before. Just like to lift a ball up into the air, I would have to do a positive amount of work. I would have to add energy to the ball. Okay, if I want to take a positive charge and move it up in potential, I have to do a positive amount of work. Okay, and so the work required by an outside force to move a charge little q from a potential V1 up to a higher potential V2 is given by this equation. And this should look very similar to what I wrote before. So the work done by an outside force in moving a charge little q from a potential V1 to a potential V2 is given by this equation. Okay, which again should make complete sense because it's basically just the definition of potential difference that we saw before. Okay, but keep this equation in your mind. We'll do some examples here momentarily. Now, let's say I take a positive charge out of my pocket, I lift it up from a low potential to a high potential. And let's say I let it go. Okay, now in your mind, picture the ball. If you lift a ball up into the air and you let it go, of course what's going to happen is the ball is going to fall. And what's going to happen if you drop a ball is it's going to lose gravitational potential energy and gain kinetic energy. Likewise, if you take a charge out of your pocket and you move it to an area of high potential, it's naturally going to fall down to an area of low potential, and in the process it's going to gain kinetic energy. Okay, I should point out at this point that if you take a negative charge out of your pocket and you let it go, it's going to try to go up in potential. The analogy doesn't work so well with gravity because there's no such thing as negative mass, but I guess the analogy would be if you take a ball out of your pocket and it flies up into the air, which is kind of counterintuitive, but again, there's no such thing as negative mass, there is such thing as negative charge. But anyway, my point is that the electric field can itself do work, just like the gravitational field can do work on a mass. The electric field can do work on a charge. In this case, the work done by the electric field, so this is the work done by the field, misspelled field, would be given by the equation negative Q times delta V. Now notice this is very similar to the last equation we saw, W outside equals Q delta V. The only difference is this one has a negative sign. Okay, so in other words, what I'm saying is the work I have to do to lift a charge up to a higher potential, all that energy would come back out when I let that charge fall back down to a lower potential. As with last year, conservation of energy still applies. Conservation of mechanical energy still applies, especially because in dealing with problems with the electric field, you almost never have any frictional force or non-resistive forces, and so conservation of mechanical energy still definitely applies. The work energy theorem still applies, and remember that the concept of work is the transfer of energy to or from an object, okay, or in this case, to or from a charged particle. Okay, so if you keep these things in mind, we'll do some examples, and then hopefully as we do the examples, everything will start to click a little bit more. Okay, so charge of 15 microcoulomb is moved from point A, having a potential of 18 volts, to point B, having a potential of 25 volts. This looks just like the one that we did a minute ago. But now the question says how much work is done on the charge in moving it from A to B. Well, that calculation we've already done. Okay, the work done by an outside force would be equal to Q delta V, and so that would be 15 times 10 to the negative 6 times the potential difference, which was 7 volts, and we already did that calculation before. Okay, that is 1.05 times 10 to the negative 4 joules. Okay, in other words, that's how much energy I have to add in order for the charge to move from point A to point B, because point B is at a higher potential. Basically, I'm lifting the charge up to a higher energy level, and so I have to fight against the electric force acting on the charge. Because remember, electric field points from high potential to low potential. So in other words, there is an electric field out there, just, not because of little q, because of some other charge configuration, but there's some electric field out there driving the charge from point B to point A. In order to move it from point A to point B, I have to fight that field. Now, let's say I move the charge from point A to point B, and I let it go. The next question says when the charge is released, it travels from point B back to point A. How much energy does the charge gain from the electric field by the time it reaches point A? Okay, and if you've been paying any type of attention, you should realize, of course, that the answer has to be 1.05 times 10 to the negative 4 joules. Why? Because that's how much work I had to do on the charge to get it up to point B. When I let it go, all of that energy comes back out. Okay, it comes back out in the form of kinetic energy. So in other words, you would have to add this much energy to little q to move it from A to B. If you let it go, all the energy comes back out. It's just conservation of energy all over again. Okay. When I lifted it up from point A to point B, I was storing it in terms of electric potential energy. When I let it go, all that electric potential energy transfers back into kinetic energy. Okay. But the value is the same because energy is conserved. Okay, so let's take a look at some examples, some more complicated examples. Okay, a proton is initially at rest, a proton initially at rest is accelerated between two parallel plates through a potential difference of 700 volts. Okay, so we have two parallel metal plates, and they are charged. And I do want to remind you that this type of charge configuration has a constant electric field. Okay, the two charged parallel plates, the capacitor setup is what it's called. I also want to remind you that electric field lines always point from high potential to low potential. Okay, so based on the diagram, I'm looking at this, and I know that the left plate has a potential of 200 volts, the right plate has a potential of negative 500 volts. So the electric field lines in between these two plates would look something like this. They would be uniformly spaced out to represent the fact that the field is constant. I didn't do the best job drawing these. These should be evenly spaced out. Just ignore my bed handwriting, and of course there would be some edge effects at the sides. Okay, now it says the proton. Right away when you see that, you should think, okay, well, I know the charge of the proton. The charge of a proton is 1e. Okay, that is 1 times 1.6 times 10 to the negative 19 coulomb. Okay, that's the elementary charge. And it says initially at rest is accelerated between parallel plates through a potential difference of 700 volts. Now, where does the 700 come from? Well, going from 200 to negative 500, that's a potential difference of 700 volts, right? What is the maximum speed reached by the proton? So, if we put a proton at the left plate, it is going to feel a force to the right, because positive charge feels a force from high potential to low potential, right? Now, what's going to happen is the electric field is going to do work. And the work done by the field, well, I misspelled field again, is negative Q delta V. That's going to be negative 1.6 times 10 to the negative 19. And here the potential difference is actually going to be negative 500 minus 200. And if you want to know why, potential difference, anytime you have a change in something, it's always the final value minus the initial value. So in this case, if you put the proton on the left plate, it ends up on the right plate, the final potential would be negative 500, and the initial potential is 200. Okay, so notice here that the negative signs cancel out. And so you find that the field, the work done by the field, is actually going to be a positive value. In my calculator, I do 1.6 times 10 to the negative 19 times 700, and the negative signs cancel out. And I get 1.12 times 10 to the negative 16 joules. That is how much work the electric field does on the proton. In other words, the proton gains energy from the field. Okay, how much energy does it gain from the field? It gains this much energy. Now, what type of energy does it gain? Well, it gains kinetic energy. In this question, we're asked what is the maximum speed reached by the proton. If the proton was initially at rest, that means that the initial speed of the proton was 0. We can find how fast the proton is moving now because we know that kinetic energy is 1/2 mv squared. And we also know, because of the work energy theorem, that the net work done on any object is equal to its change in kinetic energy. We know how much work was done on the proton. It's this number over here. So 1.12 times 10 to the negative 16. And the change in kinetic energy would be 1/2 mv final minus, 1/2 mv final squared minus 1/2 mv initial squared. But Vi is 0 because the proton was initially at rest. In other words, the proton had no kinetic energy to start with. The amount of kinetic energy it has now is equal to how much energy the field just put in. And so as long as we know the mass of the proton, we can easily solve for V final. The mass of the proton, I guess I will look that up momentarily. That, of course, would be given to you in the data booklet. The mass of the proton is about 1.67 times 10 to the negative 27 kilograms. And so if you plug that in for the mass of the proton, you can find VF just doing a little bit of algebra, plugging in the mass, rearranging. I'm just typing it into my calculator right now. Let's say I'm going to divide by the mass, and then I'm going to do the square root. And I get a number that rounds to 3.7 times 10 to the 5 meters per second. So the answer there was C. Okay, so pause there if you need to look at that some more. I would say this type of calculation is a relatively generic type of electric potential problem, you should easily be able to do this type of problem. Okay, so I'm going to erase this and we'll look at just a couple more examples. Okay, example 2. A moving proton has 6.4 times 10 to the negative 16 joules of kinetic energy. The proton is accelerated by a potential difference of 5,000 volts between parallel plates. Okay, so remember that electric field always goes from high potential to low potential. Alright, so if I'm looking at this diagram correctly, the electric field should be going to the right, like so. In other words, when this proton is shot in here, as soon as it enters the space between the two plates, it's going to feel a force. It's going to feel an electric force, which means it's going to gain even more energy. Alright, so keep that in mind. Okay, because the direction of the field is important. We're asked, basically half-assed, does the proton emerge from the parallel plates? Okay, so we know that the work done by the field would be negative Q delta V. It's a proton, we know the charge of a proton, that's 1.6 times 10 to the negative 19 Coulomb. The potential difference here would be negative 5,000 minus 0, which is still negative 5,000. And that's going to be a positive number. And so I'm just typing this into my calculator right now. I get 8 times 10 to the negative 16 joules. And I also know that the work energy theorem says that the net work done on an object is equal to its change in kinetic energy. I know how much work was done. That's 8 times 10 to the negative 16. Change in kinetic energy is 1/2 mv final squared minus the initial kinetic energy, which would be 1/2 mv initial squared, but I actually don't need to write 1/2 mvi squared because I'm actually given the initial kinetic energy right here. Okay, so I can just plug that in for the initial kinetic energy. And so from here, I just need to do a little bit of math. I do want to remind you that the mass of the proton is about 1.67 times 10 to the negative 27 kilograms. But if you plug in that mass correctly, you should easily be able to solve this equation for V final. Okay, so try to do that now. Okay, so if you did all of that correctly, then you should get a value that is approximately 1.3 times 10 to the 6 meters per second. So the answer should be C. Okay, keep in mind you are expected to know the charges and masses of common particles like protons, electrons, alpha particles I've seen before. Okay, so pause it there if you need to look at that some. Okay, so I just want to take a look at one more example. I want you to try to do example 3 on your own. Okay, I will just give you some information and get you started on this problem, and then I want you to try to do this on your own. The mass of an electron is about 9.11 times 10 to the negative 31 kilograms. And let's see, what else can I help you with? Remember, electric field lines always go from high potential to low potential. Okay, so in this case, the electric field lines are actually going to the left between the two plates. Electron comes in, enters between the two plates, and all of a sudden runs into an electric field. And you might think that that electric force would be pushing the electron back. But remember, the electric field always points in the direction that a positive charge would feel a force. Okay, the electron has a negative charge. And so when it enters this region between the two plates, it's actually going to be accelerated even more. In other words, it's going to hit the plate on the right, moving faster than than it was originally. And so it's going to gain speed as a result of this electric field. Okay, so keep that in mind. I want you to try to do this calculation on your own. Okay, really briefly, I will just outline what the work for this should look like. The work done by the field would be negative Q delta V. That would be negative 1.6 times 10 to the negative 19. The potential difference would be 250. Okay, and so I can calculate the energy gained by the electron is this many joules, and then I can use the work energy theorem to calculate how fast the electron is moving after it gains this extra energy. Okay, in other words, I'm looking for V final. I'm going to plug in the values for the masses and VI, which is given right here on my own, but V final should be, let me just see. Okay, do be careful when you're entering these values into your calculator that you're entering them correctly. And just a suggestion on some of these values, keep in mind that you cannot get a number bigger than the speed of light. And so if you ever end up with something bigger than the speed of light, that might be a sign that you made a mistake. Okay, the speed of light is about 3 times 10 to the 8 meters per second. Okay, and the value I get for V final is approximately 1.2 times 10 to the 7. Did I do that correctly? 3. Yep. Times 10 to the 7 meters per second. Okay, so this electron has gained quite a bit of energy going between these plates. Okay, so hopefully that's the answer you got. As always, please let me know if you have any questions. I'll see you guys in the next video.